Okay, so welcome to the last pair of lectures. And now that the school is well underway, it's probably good to try to make a few connections between the different things you're hearing. So when we first talk about this topological field theory that I wrote up last time, the first reason why people introduced it was to make fractional statistics, and we'll see how that works. But one thing we'll see along the way, this theory is scale invariant in an even stronger sense than the conformal field theories. So conformal field theory means basically that the theory transforms in a simple way under changes of length scale. So for example, when you rescale, your field just picks up some factor, which is a power of the rescaling. So if you like, your theory and your fields are in a simple representation of rescaling, or the conformal group. Topological field theory is an even stronger statement. The theory we wrote down is actually first order in derivatives, and as a result, the Hamiltonian is just zero. There's no finite energy scale, and it sounds trivial, but actually it's not quite trivial. But it is topological, which means it doesn't depend at all on length scale. It doesn't have any, if you like, all the energies are either zero or infinity, because any finite energy would sort of imply a length scale. So this is a very strong kind of scale and metric independence. So the theory I wrote down, and let me write the Lagrangian density. And this time I'm going to write it with a free parameter, and we'll try to figure out what this number gamma has to be for it to do what we want. And for some reason in my notes I've switched to Greek. So this A is a U1 gauge field, and if you ask what A means, I will try to make that clear in a moment, but it is different from Landau-Ginzburg theory. The field in like the theories you were hearing about yesterday, that's like a magnetization density or something like that. It's an order parameter field. Here this is not, and in particular because this has some gauge symmetry, A itself would be a little bit ambiguous. But what we're going to do with it eventually is couple it to some quasi-particles. So if I were just interested in the ground state, I would forget this term. But the original reason why people like Gervin and McDonald wrote this down in the quantum Hall effect was they wanted a theory that would do something nice related to fractional statistics when they added quasi-particles. So let's figure out what that is. But first, the gauge transformation I told you, let's write it as A mu goes to A mu plus d mu chi, U1 gauge field. And this theory is called the Abelian-Chern-Simons theory in 2 plus 1. Okay, so when we make that gauge transformation, how does this object behave? And this is the last thing I said last time, which is that it's only gauge invariant if I don't have a boundary. And that's going to lead us to what's maybe the most interesting connection between these field theories and conformal field theories, which is called the bulk edge correspondence. Basically, if one of these theories is on a manifold with boundary, it has some interesting edge dynamics. And believe it or not, that actually led to an experiment. And that experiment is probably the best prediction to come out of these topological theories that we couldn't get from wave functions and things like that. And the fact that it worked makes us think that we do actually understand something about the fractional Hall effect. So even if this seems like some just diversion into field theory with no purpose, it did actually lead to a historically important experiment on edges. Okay, so anyway, the gauge transformation. Let's just plug that in. So we're going to have one term where the gauge happened in the second field, and that term is easy. And that's going to give me 0 because this epsilon is antisymmetric under any change of indices. So because this part is even under changing those two indices, that will give me 0. But then I've got a part which is epsilon u nu lambda A mu, well, now I just have left the d mu chi, d mu a lambda. And for the second part, so this part is 0. Well, okay, the change is 0. The second term is 0. This is what I had before. And this term, I can rewrite as epsilon mu nu lambda d mu of chi d nu a lambda, because the other term I would get where this derivative acts there is going to be 0, again, by the evenness of partial derivatives and the oddness of that. So this is what I mean by a boundary term. Okay, so get rid of that now because I dealt with it, get rid of that. So what I get after the gauge transformation is what I had before plus something that is only a boundary term. So that means I'm okay if no boundary. And what this theory does with no boundary, we'll talk about, I'll at least quote the result, and it's quite amazing. Winds up being useful to mathematicians sometimes. With boundary, we have a problem. Because we do want our physical theory to be gauge invariant. So remember that later on, because that's what I said. It starts off looking like a problem, but turns out to be a feature and actually to be a connection to conformal field theories. Okay, so why did people write down this theory? Okay, so what happens if we had a Maxwell term instead of a Chern-Simons term? We know that Maxwell, a static charge is a source of electric field. How does it work here? Okay, well, to figure out the equivalent of Maxwell's equations, we should figure out the equation of motion of this theory, which means varying with respect to A. And what that gives you is, well, so if I vary this theory with respect to A, and then if I need to, I can use an integration by parts, which is why I get 4 instead of 2. I will get that d nu a lambda is j mu. And for the static charge, okay, so we're in 3 dimensions, so we've got sort of J0, J1, J2. J0 is like a charge density, so let me just focus on the mu equal to 0 version of this equation. And then what I get is, if I have 0 for this field, then these must be 1 and 2. And what I'll get is that the integral, if I integrate both sides over space, d1a2 minus d2a1 is just bringing over the 4 gamma to the left, and it looks like I forgot a minus sign there, integral d2x j naught. And this equation, so what does it mean? Well, this is like curl of A, which is B. And again, we're in 3 dimensions, so there are 2 electric fields in the plane and 1 magnetic field, which is out of the plane. This is proportional to quasi-particle density. And we call this flux attachment. The point is, this means that the way quasi-particles are sources for fields is very different in Chern-Simons than in Maxwell. It says that if we put down some density of particles, what we should think of happening, so I've got some J naught, which is the density. This is attached some amount of magnetic field to the particle. Now that magnetic field, well, it will be seen like a magnetic field for these other particles. But note, around any density of particles, I attach the field where the particle is sitting because these are both the same spatial integral. So what we've done is very much like what I was talking about with composite fermions, except here it's a real calculation in the field theory. When I put down a particle in Chern-Simons, it doesn't produce electric fields in the plane. Instead, it grabs some magnetic flux. And the amount of magnetic flux it grabs is described by this 1/4 gamma. And that's why people invented this theory, or okay, that's not why people invented the theory. It's why people started using it in condensed matter, because it was a trick where I could start with bosonic quasi-particles with no statistics. But this is saying I produce a little Aronoff-Bohm flux every time I add a particle, and that will look like when other particles move around it, that will give me some phase. So this is a way of transforming my bosons into some other kind of statistics. And what other kind of statistics I get is determined by this number. So now we can go in and choose gamma to get whatever statistical angle we want. And if we want quasi-particles to have statistics of 2π/3, for the Laughlin states, say, that tells us what gamma has to be. And if we work out the factors, the statistics angle is 1/8 gamma, the way the proportionality between flux and angle works. Basically, when you want an exchange is not moving all the way around, an exchange is moving halfway around. That's why we went from 1/4 gamma to 1/8 gamma, if you care. Okay, so that's the original feature why people were interested in this theory, but it turns out to have a number of other neat properties that we're going to talk about quickly. So let me tell you what we're going to say, and then we'll do it. So first, what if we solve the theory without boundary? And this is an example of how even though a theory might have zero energy, it can still have some interesting information. And with boundary, I will sketch how that leads to the chiral Luttinger liquid at edges. Well, so the idea is we're going to mimic, okay, so the way we normally think about braiding, let's say we took fermions, if we moved fermions halfway around each other, or maybe think about one fermion here and think about another fermion going like that, I would get a phase factor of pi, or in other words, a -1. If I moved all the way around, I would get a phase factor of 2pi. So exchange is half, braiding is all the way around. What we're doing here is saying, okay, now suppose that instead of fermions, I had bosons living in the plane, but every boson had attached to it some amount of flux. So we call this statistical gauge field, if you like. So this is kind of what A is good for. The way the equation of motion for A works is that every one of my quasi-particles, whose density is described by this, now even if it's sitting still, it doesn't have any electric fields. It's got some kind of magnetic field attached to it. And that means that I still have, remember that quasi-particle coupling, that's what appears in the equation of motion for J. That says that these particles still see electric and magnetic fields when they move around, which means if I take another particle, say over here with another one of these, and I move these around each other, well, the particles are still bosons by themselves. So they don't really see each other, but they see the flux that's attached to the other one. And that's where the phase comes from.
Okay, but you also said that two-dimensional system is crucial, but you haven't said nothing about it in your way.
Oh, sure I have. Well, here, for one thing, Chern-Simons theory doesn't even exist in 3 plus 1D. Because if you think about how I wrote it, in order to make it topological, I need to have a total of dimension 3 for those fields. So for example, if I wanted to make a theory that was scale invariant in 40, okay, so my claim is that I cannot make a theory that does this in 3 plus 1 dimensions. And maybe another sort of simpler argument why. So Chern-Simons only exists in odd space-time dimension. An argument why it was kind of crucial here that these magnetic field lines, this is like a BZ. You know, the way this works, this is like curl of A in the Z direction, and Z is not a direction we can move in. So I would have no way of moving these particles out of the plane to kind of look for the rest of this field line. So I think it is important that they're constrained to move in the plane. But maybe the simple answer is there's no theory I can write down with these properties in 3 plus 1. So it is pretty specific to 2D. Flux attachment, let me think if there's anything like it. Yeah, in 3D, if you want to do something similar, what you have to do is have one kind of particle that's point-like and one kind of particle that's line-like. And then they can have non-trivial statistics. And an example, that's what happens in 3D ZN gauge theory or in 3D BF theory. But the details are a lot more complicated than this, I will say. So I think that's all I can say. Good. Any other questions on what we're doing so far? Or let me start on this list. And then, yeah, third, we'll talk about the Hall effect, basically. Does this have the right electromagnetic response? But that's actually quite an easy calculation. And note, this means that if I want, if I took theta equal to 1 over 8. So if I remember, the definition of gamma is what appeared, well, 2 gamma was what appeared in front of the action. If I take then that will be 1 over pi by 6. So let's make this over 2 pi. Okay, well anyway, by adjusting theta, I can adjust gamma and vice versa. So gamma is fixed by what kind of theory we're trying to describe. And at the end, that will lead us to the conclusion that if we want the simple statistical angles that correspond to the Laughlin state, there are only some values of the prefactor that I can choose. So let's say, what about theory on? Well, instead of thinking about the full two-dimensional space, let's think about some two-dimensional closed space times time, which will be R. So how do I solve this theory? And this is kind of amazing because it turns out that even though this is a 2 plus 1 dimensional gauge theory, we can solve it. And there's only one piece of information it can have. So the spectrum, well, from what I claimed before, it will have to have energy equal to 0 because this theory doesn't have any finite energy scale because the Hamiltonian is 0. The Hamiltonian is 0 because it was first order in time. So if you go through the process of converting from Lagrangian to Hamiltonian, you'll find that H is 0. So the only information is really how many energy equal to 0 states are there. So to solve this theory, this is a fun little calculation, but I don't think we have time to do it. It's basically just realizing that there's a whole lot of gauge freedom, and by a sequence of gauge choices, I can actually go from this 2 plus 1 dimensional field theory to a problem of a particle moving in a magnetic field, basically a 0 plus one-dimensional field theory. And what you find is what's sometimes called topological degeneracy. You find that the number of zero energy states for then the ground state degeneracy is k to the power g, where g is the genus of M. So let's go back and try to connect everything together. So if I take this factor in front, k equal to 1 would be ordinary fermions. And we're going to think that that is a description of just the integer quantum Hall effect. K equal to 3 would be the nu equal to 1/3 Laughlin state. So what this tells us, well, k equal to 1 is kind of trivial. And if I put the theory on a sphere or a torus or whatever, it's not degenerate. And that kind of makes sense. I could figure out the Landau level on the sphere or the torus or whatever and fill it up, and that's the only state. But what this predicts, and you can see this by doing exact diagonalization of the Laughlin state and seeing that it's non-degenerate on the sphere, but when you put it on the torus, you get some degeneracy. So here this number genus is like 0 for sphere, 1 for torus, 2 would be for like a figure 8 made into a donut with 2 holes. The only case where I've ever done the calculation myself is for the torus, I should say, and the sphere. For the torus, you'll find that there's a 3-fold degeneracy of the Laughlin state on the torus. So in other words, when you put this field theory on a manifold that's closed, what information can it have? Well, it can't have anything about the size of the manifold because it's topological. So what it can have is only information about the topology, and the only information really about the topology of a closed 2 manifold is the genus. So there's a fancier version of this, which is actually what won a Fields Medal, at least a big part of what got a Fields Medal for Edward Witten, was a much deeper calculation, which I will just mention in case you like mathematical physics. Suppose we did the same thing but on a more complicated manifold that was really 3-dimensional, not just a product of a 2-dimensional manifold in the line. So side remark is that Witten, the famous paper is called Quantum Field Theory in the Jones Polynomial. The point is that Chern-Simons theory on, if you go and look at the complement of a knot in 3 space. So in other words, in 3 space, make some complicated knot, like a bunch of lines. Well, one line, I guess, twisted around, but it could be knotted up in some complicated way. And cut that out of R3. So this will be complicated if the knot is complicated. This is related to a famous invariant of knots, famous topological invariant. The Jones Polynomial, which had previously, just a few years earlier, won a Fields Medal for von Jones. And this was kind of the beginning of what's sometimes called quantum topology, where quantum in this sense means you're kind of doing a path integral over all the different ways of having fields on some manifold, and that tells you something about the topology of the manifold. So this is a much fancier version of what's maybe the more physical case here. But you could say even this is not very physical because most experimental samples are not a sphere or a torus. Usually your 2-dimensional, in fact, as far as I know, always, your 2-dimensional electron gas lives in some finite region of the plane with the boundary. So what if we replace this calculation with something like a disk? Where disk means something like finite circle for space. Time is still R. Well, from what I told you before, we could see from the gauge transformation, there is some extra bit of the theory. I need something extra piece for the theory to be gauge invariant. And what is that extra piece going to be? And here maybe I will try to sketch the calculation quickly, because this is going to be the connection I mentioned between our kind of field theory, topological field theory, and conformal field theories in the other class. Basically, the idea is that this problem that the bulk is not exactly gauge invariant. It's gauge invariant except for a boundary term. That means there has to be some extra field, some extra theory at the boundary. And that extra theory physically turns out to be a CFT, and we can actually measure it by tunneling into the edge. So the part of that I think I can calculate, let's try to figure out what theory should exist at the edge for the whole theory to work, for the whole theory to be gauge invariant. And this is sometimes called the bulk edge correspondence. This would be the field theory version. You can also make other versions at the level of wave functions and things like that. So one feature of many topological bulk theories is that they have to have some kind of gapless boundary theory. So for example, we said that the integer Hall effect has some kind of edge where the charge gets pumped in like the Laughlin pumping argument. The topological insulator has a so-called helical edge, like in 2 dimensions it's electrons going in both directions, and in 3 dimensions it's something like a Dirac cone for the surface state. So those are kind of non-interacting examples of the bulk edge correspondence. Here, we're trying to make a version for the fractional quantum Hall effect. And if I just gave you the Laughlin wave function, it's not very easy to read off anything about the edge. You could sort of convince yourself that there still had to be an edge. But how is the edge similar to or different from the integer state would not be very obvious. So we want to find something non-trivial about the edge that's different between the different fractional states, say. So the idea is going to be that the edge, and this is maybe a paraphrase of things from Xiaogang Wen, we can use the edge to measure the topological order of the bulk. And let's see how that works. Okay, so we can start with what was the part that we didn't know what to do with from the bulk. Just give me 1 second. Okay, good. Yes?
What do you mean when you say that the ground state of the quantum Hall effect is not the shadow?
The integer quantum Hall effect, if I have no boundary, like the integer Hall effect on the sphere or something, let's think about what does that look like? Well, on the sphere, okay, so I put magnetic field like a monopole at the center of the sphere, and there are Landau levels, just like in the plane, except now there's a finite number of states because the sphere is finite. And you will find that the integer Hall effect is basically filling up the lowest Landau level or some integer number of Landau levels. And with these 1 electron states, there's only one way to fill up the lowest Landau level. If I go on the torus, similarly, there's a lowest Landau level on the torus, and if I fill that up, That's the integer Hall effect on the torus, but there's only one way to fill up that finite number of states.
If I have a certain number of particles, I can shuffle them around to these levels.
You mean if I've got...
Not enough now the particles feel the first level.
But then I wouldn't have an integer Hall effect. Then I would, like if I only fill up, think about the plane. If I only fill the first Landau level halfway or something, that's not an integer Hall state. At most, it could be some fractional state. So the fractional Hall effect can have degeneracy, but the integer Hall effect is just filling up a Landau level, and that won't be degenerate. Is that making sense? Because I want to have a gapped topological state, and at the 1 electron level, that's filling up the Landau level. Yeah, I guess this is saying that both the integer and the fractional states have a gap in the bulk, but what you will notice, so for example, here's the numerical calculation one could imagine doing. You can do magnetic field on the torus and figure out the lowest Landau level states. And if you fill those up completely, then you're done. That's an integer state. What happens if you fill up 1/3 of the lowest Landau level on the torus? If your system is finite, what you'll usually see is some kind of splitting. You'll have lots of excited states up here, and then you'll have some 3 low-lying states below the big gap. And on a finite torus, with finite range interactions, these will not be exactly degenerate. So it's not like a symmetry, where a symmetry would give you exact degeneracy even in finite size. The way these topological degeneracies work is when you do your numerics and you make the system larger while keeping the interaction range finite, then you see that these become more and more degenerate. So if you like, it's a degeneracy that emerges in the topological limit when the system is much larger than the interaction length, as opposed to a symmetry breaking degeneracy, which is exact even at finite size. Okay, good. Yes?
This is a theory only for advanced, right? You cannot see it again.
Yeah, I mean, I guess you could see that it has a gap in the sense that there's no low-lying energy levels. But yeah, if you like, the topological field theory is describing the limit of the system where the size is larger than finite length scales. I guess that's saying the real world is certainly not topological. We have finite energy scales and so on. So if you like, we've gone to the limit where the physics below the gap is what matters. So when we say zero energy and infinite energy in the theory, you should really think about the infinite energy as like the gap energy. Yeah.
Sorry, so we wrote down some theory which gives us fractional statistics, and then we say, okay, but it doesn't describe the boundary actually, so we have to come up with a new theory for boundary, but why maybe we just have to write a different theory which is more proper.
Well, I'm going to show that this theory implies a theory at the boundary. We can actually derive that. And then we can do measurements, and we can say, do our measurements on the theory, on the edge of a quantum Hall sample look like what this theory predicts? And it turns out that they do.
Yeah, but
Maybe we got lucky. That's kind of, that's the way physics works in general, I would say. Like the standard model seems to agree with a lot of measurements, but it could be that we have it completely wrong and there's some other theory that would agree with even more measurements. That is a depressing thought, that the best we can do is ever agree with the measurements we have. But I would say the one thing I will say is, we'll see in a moment, this leads to quite a surprising prediction that turned out to be true, and it was predicted before the experiment. So in that sense, at least, it was a prediction rather than a postdiction, which is slightly more impressive. But yeah, let's see. Okay, so maybe I should map out where we're going. The way this is going to work is that the specific theory I get at the edge depends on K. And there's another way to look at it, which is to work the other way and ask what kind of bulk. There are some edge theories that would normally fail to be conformal. It turns out they would generate a mass. This is mostly true for like non-abelian principal models. But it turns out that there is a bulk that you could use to keep the edge gapless, and that bulk winds up looking like a quantum Hall state. Anyway, maybe that's farther off than I want to say. So, all right, let's go ahead and do this calculation and then ask me again if it seems unconvincing. But yes, it's true that all we can say is that, okay, I would say the topological field theory gets the simple things right, like fractional charge, fractional statistics, fractional Hall effect. It gets one not very simple thing right, which is the way tunneling into the edge works. And it can be derived in the integer case microscopically. I don't know of any very good derivation in the fractional case. So in other words, in the integer case, with a lot of work, you can try to start from electrons in a Landau level and integrate them out and get a theory that looks like this. The challenge in doing that is that because we start with a Hamiltonian that has finite energies, we have to find a limit where there are no finite energies. So that kind of deriving a topological field theory from a microscopic non-topological theory is always a little hard. But yeah, let me tell you the most convincing evidence that it works. Okay, so we've got this gauge problem, and we could write that as I need to choose, okay. So I said that this theory had some gauge invariance. I'm going to choose a theory where the zero component of the gauge field is zero. Choose a gauge where the zero component is zero. Then the equation of motion leads to basically curl of A is zero, and that means I can write A as the gradient of something. And this something, so in other words, what I'm saying is I can find a gauge where A is a gradient of a scalar field. And this scalar field is going to turn out to be a free boson that lives at the edge, but it's a somewhat unusual free boson because it only works in one direction. So our bulk theory so once I've gone to this gauge, I don't have mu nu lambda anymore because A0 is 0, so the only terms I have left are like this, because only the spatial components of A can be non-zero, which means the zero component must have appeared in the derivative, d2x dt. So now I need a couple of steps to sort of shuffle derivatives around, but that's all I'm doing. So I go ahead and write this out. Okay, so for example, AI is di phi. So I've got one term which is xy minus yx. So I've got dx phi, d0, dy phi. Minus dy phi, d0, dx phi. With those integrations. Just two more steps. Now I take this, and I want to write it as total derivatives that I can move to the boundary. Because even though we started off with this boson in the bulk, the point is its action can actually be moved to the boundary. So that's minus k over 4 pi. All right, so there, let me write this as dx phi d naught dy phi minus dy phi d naught dx phi. Again, same d2x dt. So what I did here was I will get one extra term, which is phi d naught dx dy phi, but I'll get the same thing from here, so those two will cancel out. So this is indeed equal to that. But now, what is this? This is like the curl of a vector, if you want. It's dx of a y component minus dy of an x component. So this is like minus k over 4 pi integral curl of v z component d2x dt, or minus k over 4 pi integral of v dot dl dt, where v is the vector phi d naught dx phi, comma, phi d naught dy phi. So in other words, the bulk theory in this gauge is exactly, well, -1 times some theory that lives at the edge. All right, so the way we normally write this theory, let me do one integration by parts to make it look a tiny bit familiar. So what we've gotten is that S edge, or if you want, you could think of it as the theory we should add to fix the gauge problem of the bulk, will be like k over 4 pi. I'm going to use an integration by parts to move one of these derivatives there. And let's just assume that the edge runs along, some region of the edge runs along x. So you could view x as the component along the edge. And I've got a funny sort of free boson theory. It's at least got two derivatives. But let's compare how this theory is similar to or different from the free boson theory you're used to. So this is 1 plus 1 dimensional boson. But it isn't what we're used to, which would be like d0 phi squared minus, say, dx phi quantity squared. That would be the normal free boson CFT. This is like a chiral or topological version of that. And let me replace 0 by t now. Okay, so why do I say this is topological? Well, this theory came out of a topological theory with energy equal to 0. So this theory has to have energy equal to 0, which it does, because again, the Lagrangian is first order in time, which means the Hamiltonian will be 0. It's also different from this theory. This theory has modes going in both directions. If you like, it's got modes that are like x minus t and x plus t. This is called a chiral boson. It only propagates in one direction. And, oh, well, okay, the way it's written now, it doesn't propagate at all. But once we add a velocity, then it will move in one direction. And so what we assume is that, okay, this is the part that is forced by the bulk. And it's got some prefactor which came from the bulk statistics angle. But this theory would have energy equal to 0. We know that in practice, when we make the boundary of a sample, the velocity at which the edge modes move depends on how steep the confining potential was, which is some non-universal physics. So let's add some non-universal term to give this a velocity. But then you could say, well, that sounds like cheating. So is there anything I can measure that doesn't care about the non-universal stuff I added and just cares about k? Let's do that. And the answer is yes. Good. So let's add a non-universal velocity. And the number v does not come from the bulk. That comes from details of the edge physics. And this is the free chiral boson theory, as it's called. And you can view it, if k is equal to 1, this is a bosonized version of a free fermion moving one way. So this is the prediction that there must be some theory like this. And in general, if I had multiple components in the bulk, there would be multiple components at the edge. So what could we measure that would only depend on k? And for that, you need a little bit of condensed matter physics. If we tunnel electrons into the edge, what we basically wind up measuring is the correlation function of the electron operator. So to be precise, the current voltage curve is related to the scaling dimension of the edge operator, of the electron operator in the edge CFT. In other words, it's determined by the same number we saw yesterday. If I look at psi electron of 0, psi electron of xt, that falls off as some power in xt because the edge is a scaling theory, conformal field theory. And that power, the way that the electron scales at the edge, is only determined by k. It doesn't care about the velocity, which makes sense because the velocity, it tells me, if you like, the units involved in converting between x and t, but it doesn't change any powers, while k does actually change powers if you work out the details. And what this, if you want a more physical explanation, k equal to 3 was the Laughlin state where the quasi-particle had fractional charge. The electron operator scales very differently because the electron breaks up into 3 quasi-particles. So the prediction well, the integer quantum Hall effect has an edge that's basically free chiral electrons, and that gives you, maybe not surprisingly, ohmic tunneling. And the nu equal to 1/3 fractional quantum Hall effect, well, is predicted to give I going as v cubed. So in other words, it's not a gap at the edge. The edge is still gapless, but it's a power that is very different from what you normally see when you tunnel into a metal, into a gapless system. And in general, you can make other quantum Hall states and get predictions that I goes as some power. And these are the predictions that mostly work. I won't claim they're perfect. So for example, at 1/3, maybe the value is 2.8 experimentally or something. Measuring a scaling law over many decades in voltage is not that easy. But it's massively different from 1. And this is, I think, a big part of Wen's piece of the recent prize that went to Wen and Kitaev, was this prediction that if you want to know something out of Chern-Simons theory that no one had gotten before just from staring at the wave function, it's what people see in edge tunneling exponents. So the more general connection in this bulk edge correspondence, so we've done kind of the simplest case of one abelian theory in one field. In general, if we had a more complicated topological bulk, if it's chiral, which means if there's a preferred direction or if it breaks parity, then in general there has to be an edge mode, and that edge mode is some CFT. There are topological theories that don't have an edge mode. If I had one more lecture at the end, I would probably talk about those. I will say some references for them. So I don't want to claim that every topological theory has to have an edge. The simplest counterexample to that claim would be the Z2 spin liquid, and there's a great example of that, which is the Toric code model, which I will try to at least write up before I finish. But at least it seems like the topological theories that are chiral, that have a preferred direction at the edge, do have to have an edge mode. And here, as you can see, we could start from, with a bit of gauge fixing in math, we could start from the problem in the bulk, we could start from the bulk theory and show that what was left over was this edge theory. Or if you like, the piece that we needed to add to fix the problem was an edge theory, and that edge theory is not very complicated, it's just a free boson, except it's a free boson that only moves in one direction, because this is clearly not invariant under t goes to minus t. So maybe the last thing to say about Chern-Simons before our little break, and then we'll go back to topological insulators and some other things. Maybe the last question would be just, does this give a Hall effect? And the answer to that, the calculation that you do is essentially, if you've ever integrated out a field in a Gaussian field theory, that's all we're doing here. Because we start, okay, so we've got k over 4 pi. And I'm just going to sketch how this should work. epsilon with indices. This would be my Chern-Simons theory. And then I couple that to electromagnetism. And the form of that coupling turns out to be like a mixed Chern-Simons term, because basically the electromagnetism couples to the vector potential of electromagnetism couples to the Chern-Simons field in this form. So capital A is electromagnetic vector potential. Lowercase a is the Chern-Simons field. And again, there's some factor. And this one is called mixed Chern-Simons because it's got the two different fields in it. But now we come along and we integrate out little a. So in other words, think of this like a Gaussian integral, where I've got a squared minus little a times big A. Well, what did I expect when I integrate out little a? I can complete the square, and I'll get terms with two big A's, except that in integrating out, I'll get a 1 over k. So this will give me something like epsilon a dA, except now k is in the denominator. Let me just finish 1 second. This is the term I first introduced for Chern-Simons. This corresponds to a Hall effect that is e squared over hk once I put the units in correctly. So question, yeah.
Why do we couple capital A as in this way, but not like a long derivative, for example?
Well, so the other option would be to have the derivative act there. And if I do that, I can integrate by parts and make it look like this. So I guess maybe the way to think about this, so I think by power counting, the coupling should be of this form. The other option would be to have the derivative there instead of here, but if I have the derivative instead of there, that's actually just a minus sign difference through an integration by parts. So at least by power counting, this is the easiest way to couple to electromagnetism. You can make, if you want, you can put in, to figure out what the constant is, you need more information. So you need to specify something about the charge of the quasi-particles. But the main point I want to make is, if you were wondering, why is k in the numerator here? So in other words, k equal to 1, k equal to 3, we're actually increasing the Chern-Simons coupling when we go from integer to fractional. It's through this process that k in the numerator becomes k in the denominator, and it's just because that's how completing the square works when you do Gaussian integrals. And then when you restore the units right, you'll get e squared over hk, so that's why k equal to 3 up here, there are more details in some of the notes that I put in my list at the beginning of the class, but that's why k in the numerator became k in the denominator through a Gaussian integrating out. Okay, so I think we better take our 10-minute break, and then we'll change gears when we come back. If there are other questions about Chern-Simons, now's probably a good time, because we'll do other stuff. Yeah?
So is it after light work, you solve some classical equation of motion and you plug it in back? So are you doing some D field there?
Let's see. It's true that everything we did is classical. The only case where quantum mechanics has come in, I think, in a calculation today was in solving the theory on the torus or something like that. So I think it remains true as a relationship between quantum theories, but you may be right that a more careful derivation would be necessary to prove it.
So in the theory you wrote down current decay, but by no means you've shown that this is actually quantized, right? I mean, you just said it, but it's not really shown that it's actually, because in the beginning it's just current.
So what was the question? That
Decay in front of your action, right? So you just wrote down the Lagrange intensity and then but it was the current decay, but
well, but k came from the bulk, and k is quantized in the bulk by the requirement of fractional statistics. And k cannot be, okay, so maybe a way to state it is, have I shown that k could not be modified by the edge? So if you want, the bulk gives me a k which is quantized because the bulk statistics angle can't be quantized. The bulk statistics angle is quantized, it can't be slightly changed. And basically this theory is not something you could produce just at the edge. It's kind of anomalous in that sense. So if I gave you just a one-dimensional system that was not the boundary of anything, I don't think it's possible to make this theory with arbitrary k. It's a little bit like making the edge of the two-dimensional topological insulator without the bulk. So I sort of think, just as we said that the bulk needs the edge needs the bulk as well in order to be kind of a sensible theory. And maybe that's why there's the non-renormalization of k. If you want an interesting fact about the bulk Chern-Simons theory, so before people completely realized its topological nature, they sort of asked, well, what if we put in a different value of k that is not an integer and try to renormalize the theory? It has a very unusual renormalization behavior, which was shown by Coleman, which is that k basically instantly jumps to the nearest integer and sticks there. So it is a very odd theory if you start with non-integer k. In the abelian case, you can start with non-integer k. It turns out that in the non-abelian case, the non-abelian Chern-Simons theory doesn't even really make sense. It doesn't have a well-defined gauge symmetry because now there's the non-abelian gauge transformation is more complicated and the theory doesn't even make sense without some quantization of the coefficient. In the non-abelian case, k is called it's related to the level. Yeah.
Question. You said that k equals 3?
For the 1/3 state, yeah.
Yeah, describes mu equals 1/3. But what about the conductance, the conductivity?
Yeah, so the idea was k equal to 3. If I went through this process of adding electromagnetic fields and then integrating out little a, I would get e squared over 3h. So for the simple cases of one abelian field, like if I started with k equal to 5, I would get 1/5. But in general, that connection is not true. Like suppose you said, what about the 2/3 state? Well, the 2/3 state we actually describe with not one number k, but in general there's a so-called k matrix. So for example, the nu equal to 2/3 state, the simplest k matrix is like 1, 0, 0, minus 3. If you remember what I said about 1/3 and 2/3, I said 2/3 is like a 1/3 gas of holes in a nu equal to 1 state of electrons. So it's like this is a nu equal to 1 state, k equal to 1, but then along with it, there is a 1/3 state with the minus sign because the 1/3 state is hole-like. So in general, only for the very simple states is there a single abelian Chern-Simons field. The composite fermion or hierarchy states that I talked about in the discussion, those are generally still abelian Chern-Simons, but with a larger, but with more of these little a fields, which means a more complicated k matrix. And then the most complicated quantum Hall states would correspond to non-abelian Chern-Simons theories.
But let's take the simple Chern-Simons with only one field and a value of k. Nu in general is, and the conductivity is what?
So then, yes, so one value of k, and nu is 1 over k in the simple case, and sigma xy is e squared hk. And the way to show that is, I went a little bit quickly through it. Maybe I can say more after the break. But if you try to couple electromagnetism to the theory, you can sort of figure out what the coefficient of that coupling has to be. And then when you integrate out the little Chern-Simons theory to get a purely electromagnetic response, k goes from the numerator to the denominator. So that's kind of how this happened. Yeah.
Okay.
Good. Still more questions. Okay, sure.
What really is this lower case range? Because you said it's a U1 gauge field, but there's also the normal U1 gauge field, so there are two U1 gauge fields.
But there's also the
capital A, the normal U1 gauge.
That's right. So yeah, there are two different, one of them is there are two gauge fields and they have different physical meanings. So one of them is our real world 3+1 dimensional capital A electromagnetic gauge field. And the other, with the statistical gauge field, it's an interesting question. I think this depends on whether, what is your attitude toward reality, whether you're a Platonian or not or something. So little a, we put in as a device where we could say, let's not think about the microscopic electrons. Let's make a theory where, in principle, I would start with the microscopic electrons, I would integrate them out, and I would get only the essentials left over. And the essentials left over would be this little a. And a way to understand what little a is doing, I mean, the original way was if I put down quasi-particles, little a is there just to give me the right statistics between the quasi-particles. So whether little a, so if you want, maybe a way to ask it is, suppose we thought about Landau-Ginzburg, and you're making a theory of the Ising model in a magnet or something. So what's real are the spins in your magnet. But we kind of group those together, and we could say, okay, we're going to work with this other field, phi, which is some kind of average of the magnetization. So that's the order parameter field, but sometimes you do various field theory manipulations and you wind up working with some other field that is not the original field. That's kind of what we've done here. So a, little a, it certainly can't be like the density of electrons or anything like that, but it is sensitive to the density of electrons through this flux attachment. So I guess all I can say is we call it the statistical gauge field because we put it in order to get the simplest theory of quasi-particles with fractional statistics, but then it predicts all this other stuff, and all this other stuff seems to be correct for the fractional quantum Hall effect. So for example, it predicts topological degeneracy, edge states, things like that we can go and kind of check either numerically or experimentally. So in that sense, it seems to be the right picture. But as I said, I think as far as like so yeah, people can try this process of putting in the electrons and integrating them out and trying to write some expression for A in a particular gauge that came out of the electrons. As far as I know, that's only really done well for the integer case. There's a long paper by Yakovenko. I'm not sure that is really feasible for the fractional case. Good. Okay, last question for break.
Yes, I actually wanted to ask about the relation between K and statistics. Like, I suppose that, okay, I can multiply action on n and a number, and my equation of motions are the same, but like stress and tension maybe is different. But how K is related to the statistics? How can I see this?
Yes, well, if you remember, we said that theta, so the way I started off was K over 4 pi was what I wrote as 2 gamma instead in the first part. And that 2 gamma, that we could relate to the statistics. I said that the theta was like, 1 over 8 gamma or something. So that says K we can directly relate to the statistics of the particles with flux attached. Does that make sense? Yeah, so I guess maybe a way to put it, if I want the quasi-particles that are sources of J to have fermionic statistics, for example, there is no choice other than K equal to 1. So in that sense, I don't think, once you choose the statistics angle you want, I don't think there's any freedom left in the simple one-component theory. All right, let's take a, 5-minute break, I guess, and then we'll finish up. So I think to wrap up the main part, I might have one comment at the end on the Z2 spin liquid. But let me say a little bit about a kind of field theory for topological insulators, but it's not a field theory in the same way. It's just an electromagnetic response. But it turns out that it's quite interesting. And in fact, particle physicists thought about this kind of response pretty carefully even before the topological insulators were discovered. So in that sense, they just didn't have the material or the band structure. But I want to claim that, in a sense, the electromagnetic response of the 3D topological insulator was worked out in the 1980s by people thinking about axions. And it shows some neat connections between different kinds of terms and field theories and so on. So I'm going to go back and say more about the three-dimensional topological insulator, but maybe thinking less about microscopic electrons and just what does this material do. So let me remind you of some basic physics of this, because I only said a few words about it before. And the idea of where we're going is that the 3D topological insulator realizes what Wilczek, for example, called axion electrodynamics in solids. So that's where we're headed. So the 3D topological insulator, the first way of thinking about it from condensed matter people, well, this is a 3D band insulator. But the bands are, let's say, Z2 non-trivial. They have some invariant, and I'll actually write down a nice mathematical expression of that by the end. But let's just start with the consequence of that. So in other words, the bands, it's not Chern number, it's something more complicated in 3 dimensions, and it depends on having spin-orbit coupling and stuff like that. But there's something complicated about the band structure. And when I go to the surface, what I will have is that on every surface there's some kind of gapless state. And in the simplest materials, the surface state looks like a Dirac cone. And to be precise, they're an odd number, and let's just take the odd number to be 1. So the surface state is kind of like 1/4 of graphene, where if you've ever studied graphene, that's a 2-dimensional material which has 2 Dirac cones. In other words, there's K and K prime. They're 2 momentum points with a Dirac cone. And spin-orbit coupling is very small, so there basically is a spin degeneracy. And the 3D TI surface, if I look at one of these surface Fermi surfaces, we say the spin and the momentum are locked. For the 3D TI, there's 1 Dirac cone and 1 spin. So the 3D TI surface, in the simplest case, is like 1/4 of graphene. And that 1/4 we'll use later on. So this is definition 1 of a 3D topological insulator. It's something with time reversal symmetry and spin-orbit coupling. TRS meaning time reversal symmetry. All right, so that was definition 1. And then definition 2 is what Wilczek was talking about. And at first glance, these sound totally different. So we'll spend 10 minutes or so making the connection. And there's a little, I believe this is from 1987 or so. So we know that when we go into a solid, we modify, say, the dielectric constant and things like that. But if you have a solid of low symmetry, like a so-called magnetoelectric solid, let me imagine a term which is like E dot B, where these are just the electromagnetic E and B fields. Theta, sometimes called theta angle, is some number, and you know what E squared and H are. So the idea of this is this would be a material where if I apply electric field, I produce magnetic moment, and if I apply magnetic field, I produce electric polarization. And the most famous case where this can happen, or this is known to happen, is in materials that are magnetic. They break time reversal symmetry, and they break inversion symmetry as well. So this term, naively, breaks both inversion, because it's linear in E, and time reversal, because it's linear in B. But, so if you just wrote down that term and you thought about it the way people mostly had thought about it, you'd say, okay, if I've got inversion, then that would mean theta is equal to minus theta. Or if I've got time reversal, then theta is equal to minus theta. And either way, theta is equal to 0. But it's significant that we write it as theta, because the point that particle physicists had thought about was there's something special about E dot B compared to E cross B and so on. And in fact, we should think of theta as an angle. And this is the kind of thing we're going to explain in a moment. And I would put it in somewhat condensed matter language as the following. Okay, so, and here is where it gets a little bit subtle. Looking ahead a bit, if I gave you a gapped material and you could perform a measurement, then theta would not be an angle. Theta would be a number that you could go out and measure. But it turns out that the details of what you measure are actually dependent on the surface to some degree. What's going to happen is that the surface, depending on the details of what surface you put on, you can shift theta by a multiple of 2 pi. And we'll explain it. That sounds fancy, but it's actually pretty simple in condensed matter terms. The bulk, if you like, determines the fractional part of theta, and then the surface can shift that by 2 pi n. But if we believe this, just to start with, this already makes a remarkable prediction, because the easiest way to get something like a Z2 is to have an angle that is odd under a symmetry. So what angles are compatible with time reversal symmetry, for example? Theta equal to minus theta. Well, one obvious answer is theta equal to 0. But pi is equal to minus pi. So the point of Wilczek's paper, although it didn't, the language could probably be modernized in a couple of places, but it was that bulk materials with time reversal symmetry should actually come in 2 flavors. There should be theta equal to 0 materials and theta equal to pi materials, where theta means the coupling of E dot B in the right units. And we now agree that he was right, and those are just the ordinary and topological insulators. So I want to make a connection between having an odd number of surface Dirac cones and having theta equal to pi. And the way that field theory comes in, and for now it's a simple electromagnetic field theory, is how is E dot B related to what's going on at the surface? And this is why E dot B is very special compared to E cross B or others. You probably know that E dot B is a Lorentz invariant, but another reason why it's special so we sometimes call this F wedge F is another way to think about it, but it's the idea is that this is like dI AJ dk AL. So that will give me E dot B, and this is essentially a derivative of AdA. And this is the electromagnetic Chern-Simons that we've already said is related to a quantum Hall effect, or a Hall effect in general. So what's the physical meaning of this relationship? In other words, to say a material has E dot B in bulk, that's some bulk 3 plus 1 dimensional term in the Lagrangian. What could that have to do with the surface? Well, here's the idea. Think about what is the physical consequence of having a Hall effect at the surface of some 3D slab? So let's say that in order to do this, I would have to take my 3D topological insulator and apply some little magnetic field at the surfaces in order to gap out the Dirac cone and put them in a Hall effect state. So let's say if I were to apply electric field, then Hall effect means I'll get currents perpendicular to E at the surface. And let's say I arrange it so that the currents circulate. In other words, it's opposite Hall effect on the 2 surfaces. Then I've got electric field is producing some current running around the sample, and that will produce a B. And the inverse effect, if I were to apply a magnetic field and I had quantum Hall on this surface and that surface, before I mentioned that the Chern-Simons term implied that magnetic field would increase density. So indeed, if I apply a magnetic field, I would get extra charge here, opposite charge there, and that would be my electrical polarization. So mathematically, what this is saying is that if I had a, say, theta equal to 0, or not equal to 0 there, theta equal to 0 up here, theta equal to 0 down there, then if I had integral over the bulk of theta E dot B, which is theta derivative AdA, well, integration by parts means that I could transform that to wherever there's a change in theta, there's a quantum Hall layer. In other words, there's a quantum Hall layer here at the bottom where theta jumped one way, and there's an opposite quantum Hall layer there where theta jumped the other way. So there is, because of the magic of integration by parts, high school mathematics, there's really no difference between saying a material has a bulk E dot B coupling and saying it has a surface Hall effect. And now's where these units become important, because that means that saying that a material has a bulk theta equal to pi, that means that its surfaces don't have integer Hall effect, they have half-integer Hall effect. And this, we think, is the answer, this theta equal to pi story. You could have asked, well, if the Hall effect is quantized in the quantum Hall effect, then what's quantized in a topological insulator? And we're saying that this kind of magnetoelectric effect is quantized in the 3D TI. Right, this way. And here's where the details of the surface come in, because we know that if I had a two-dimensional surface, by changing the electron density, or you could think of it as adding extra quantum Hall layers if you want, without touching the bulk, and without going to the fractional quantum Hall effect and complicated things, even at the simple integer non-fractional level, I could add plus some n e squared over h. And this would be some surface physics. While this part, this kind of offset, is coming from the bulk. So this is what it means to say that theta is equal to pi. And there's actually some experimental evidence for this now, that if you could just look at one surface of a 3D topological insulator, once you'd applied a little bit of a magnetic field that wasn't strong enough to mess up the bulk, but was strong enough to open a gap at the surface, then you would see half-integer Hall effect. And what does that have to do with the Dirac cone? Well, here's where graphene comes in to save the day. Because you could ask, graphene, maybe for all of you, graphene is something that's always been there and we've always understood it, but I remember when graphene was discovered experimentally, how did we know it had Dirac fermions? What's a good experiment you can do? Well, one is to look at the quantum Hall effect in graphene. So I told you before that the magnetic field scales are different, but there's another difference which is more basic. So we've got our two Dirac cones and two spins in each, but we can apply a magnetic field and open up a gap and measure the Hall effect. And the answer is what you get is not 0, 1, 2, 3, 4 times e squared over h. At least if interactions are weak, you get something like this. You see plateaus at -6, -2, 2, 6, etc. So you see a funny set of integers. They can be both positive or negative, which makes sense because graphene has a kind of particle hole symmetry. But why this pattern of integers? Well, let's divide by 4 to make it a little bit more obvious. So I said graphene has 4 Dirac fermions, the way we count, because it's got 2 spins and 2 Dirac cones. And that means if we got rid of that degeneracy of 4, then one Dirac fermion is different from a quadratic fermion. It doesn't give me integer Hall effect, it actually gives me half integer Hall effect. And this is consistent with what we need to be true for this to work, because it says that this half integer is exactly what we would get from gapping an odd number of Dirac cones. So that E dot B term is consistent with the previous definition of an odd number of Dirac cones. It's just once you open a gap, odd number of Dirac cones means you don't get integer Hall effect, you get half integer Hall effect. So really we do believe that the topological insulator, the right sort of electromagnetic response, is either half integer surface Hall effect once you gap it, or theta equal to pi. And those are not really two different things, they're just the same thing because of that equation. So this actually led to something kind of neat about what is the Z2 topological invariant and why I didn't write it down before. After realizing this connection, you can ask, well, suppose I took the microscopic electrons, and this is something we worked a lot on, you try to integrate them out and figure out just what is the E dot B coupling. And it turns out that you get a Berry phase expression, and this is maybe the first appearance of the non-abelian Berry phase in solid state physics for something important. So let's put it this way. Suppose I wanted to compute theta microscopically from what the electrons are doing. So theta is, I think the precise term should be orbital magnetoelectric polarizability, which is like either dP by dB, and that's simply related to dm by dE, magnetic moment electric field or polarization magnetic field, for a band insulator. And here, in general, it's not as good as TKNN. You get both a geometric part and you get a messy part, which has energy denominators and so on. But if you have time reversal symmetry, then you only get the geometric part. So I'm just going to focus on the geometric part. So let me write some words, and then we'll see a bit more what it means. It's the non-abelian Berry Chern-Simons form. So let me say a bit. I've used this term Chern-Simons, but I haven't yet said why the mathematicians like it and how it's related to Chern number and things like that. So the history is, first there were Chern forms. That was, I think, early on, like 1950s maybe. And then later on in the 70s, there were Chern-Simons forms. Chern forms live in even dimensions. And the example we've seen so far is like F. Which starts living in d equal to 2, or in d equal to 4. There would be F wedge F, which for electromagnetism is just E dot B. Chern-Simons forms, well, the easiest example is d equal to 1. This would be, well, A, and we know A is the object whose derivative gives me F. Or if I took AdA in the abelian case, what we said before was that this was like the quantum Hall effect for electromagnetic fields. And the derivative of that would give me E dot B. So the Chern-Simons form is something that in general is not gauge invariant. It might be gauge invariant almost if I integrate it over a closed manifold or something. But its derivative is something gauge invariant, and that's the Chern form. So that's why the Chern form was discovered first. It's simpler in some ways. So this was for the abelian electrodynamic case. But in general, there is also a non-abelian version of this, which has an extra term like AAA. 3 powers of A would have the same power counting. And that is a well-known object in field theory, but it turns out it's even important in solid-state physics. So if we were talking about electromagnetic fields, this is how it would work. If we were talking about Berry gauge fields, we said that A, the Berry connection, was related to polarization, and the Berry curvature was related to quantum Hall effect. So we could ask, well, what is the second Chern form of Berry curvature related to? It turns out this is related to the quantum Hall effect in 4 dimensions. But there's also an object in 3 dimensions. This is polarization, and this is magnetoelectric polarizability. But let me show you one neat thing about how polarization works, and then it turns out the same thing is true for polarizability. And it gets back to something I mentioned earlier about gauge invariance. So how could it be mathematically that something about the bulk is like an angle? Whereby an angle means only defined modulo 2 pi. And the original example of that was the electrical polarization. And I wrote down a formula, but I said this is actually a little bit trickier than the quantum Hall formula. I said that polarization in 1D is like electric charge. There's a factor of 2 pi. And then there's the integral over the one-dimensional Brillouin zone. And I'll try to write script A for the Berry connection. So this says, if you like, polarization is something you could measure with like real electric fields applied to your system. So that is an electromagnetic response, but it's given by a simple integral over this Berry gauge field, Berry connection. But there's actually an ambiguity in this formula. The precise statement, I have talked about gauge transformations so far, but an interesting topological fact is that there are 2 kinds of gauge transformations in the world. Well, maybe there are many kinds, but there are 2 kinds for our purposes, large and small. And large, a precise term is non-null homotopic. Large gauge transformations are the ones that you cannot connect to the identity. And that sounds fancy, but here's a simple example. Remember what A was. A was psi k I dk psi k in 1D. Let's make our gauge transformation. Okay, I think I called this U before, but it doesn't matter. All right, then A goes to A minus dk chi k. So what happens to polarization? Well, that means polarization goes to what it was before, minus e over 2 pi, integral over the 1D Brillouin zone, which is like a one-dimensional torus. Let's write it, if you want, as minus pi over a to pi over a. But remember, there are periodic boundary conditions. And then I've got dk times partial k chi. So what can this be? Well, one option is that chi at pi over a could be equal to chi at minus pi over a. But that's not the only option, because I could make a gauge transformation that actually winds by a multiple of 2 pi as I go around the Brillouin zone. Because note, the requirement should be that I get the same phase factor at k and k plus 2 pi over A. In other words, if it should have the periodicity of the Brillouin zone. But because the only physical thing is this exponential, I also have this possibility. And if n is not equal to 0, then we say that the gauge transformation has a winding number. That's a large gauge transformation. It's one that I can't shrink continuously to n equal to 0. So this becomes P1d minus n times e. The 2 pi's cancel out. So that says that polarization in one dimension is actually ambiguous by an integer multiple of charge. And a way to think about that is if I gave you the same bulk unit cell, and then I terminate it and make a boundary, I could add some integer charges at either boundary without modifying the bulk, and those would appear to shift the polarization, but only by integer amounts. So the same thing is true, but in a deeper way for the non-abelian Chern-Simons form in 3+1, and that's why the theta angle can shift. So theta winds up being like minus 1 over 4 pi integral d3k of the non-abelian Chern-Simons form. Looks like a 1/3. Sorry. So the only special thing about this object is that if I took the derivative, I would get f wedge f. But now there are gauge transformations in 3D that will shift this by 2 pi. Large non-abelian gauge transformation. So what does it mean to say that there's a non-abelian Berry curvature? Well, it just means that if I've got multiple occupied bands in a solid, now I should think about, say, UKI, dk, UKJ, where I and J are band indices. So that's my now possibly off-diagonal Berry curvature. And it's often true that if I've got a bunch of occupied bands, things related to energy differences between the occupied bands sometimes don't matter. So that's how the non-abelian Berry curvature appears in some physical quantities. And the reason why, if you like topology, that this happens, it'll be known maybe to the field theorists or high energy people. So in mathematical terms, what happened here was that you can have a non-trivial winding number of a U1 gauge transformation, which is related to the fact that maps from the one-dimensional Brillouin zone to a phase, which is like a circle, unitary group of one element. These can be non-trivial, though they're labeled by an integer. We would say that the pi1, the fundamental group of S1, is equal to the integers. Here, in the non-abelian case, we should think about UN gauge transformations and maps from 3D. So all of this ambiguity of theta is related to the fact that maps from the three-dimensional torus to SUN n greater than or equal to 2 are labeled by integers because pi3 of SUN, I don't need the S actually, pi3 of UN is equal to Z, n greater than or equal to 2. But all of this is saying, just to kind of wrap up our discussion of Berry phases, is that when you want to understand the 3D topological insulator, maybe the best way to do it is this theta angle. It has a magnetoelectric effect. One reason why that's nice is you don't so much care about whether it's interacting or non-interacting. It's something you can go out and measure. But if I ask what determines theta for non-interacting electrons, it's some complicated integral, but it is an integral over the Berry connection. It's just the kind of off-diagonal in band index piece of the Berry connection. And it turns out that that integral over the non-abelian Berry connection has exactly the right mathematical properties. So this is maybe the most dramatic example of something I kind of claim as a big part of, say, Thouless's contribution, which is that every sensible mathematical object you can make out of the Berry gauge field seems to mean something. And the field theorists have spent a long time thinking about what are the gauge invariant objects you can make out of a gauge field. So all we do is we plug in the Berry gauge field to the things they've thought about, you get some expression, and then you just have to figure out what does that mean physically. But so far, we don't have many other things that are sensitive to the non-abelian part. So I think I want to make a couple of closing comments about maybe current topics in the field, or at least two things that I would cover, the next things I would cover if I had a bit more time, in case you want to learn on your own, and then I think we'll be done. So two more topics. That are, at least the first one is a bit hot because they were only discovered experimentally recently, are so-called topological semimetals, like 3D graphene. You could view them as 3D versions of graphene. Not in the sense of being made from carbon, but in the sense of having linear band crossings. And let me explain why these are kind of topologically interesting in a very simple example. Suppose I took the two-band crossing in graphene, and I didn't say much about this, but Kane and Mealy were thinking about graphene and ways to open up a gap in graphene. And there are a whole bunch of different ways to open up a gap in graphene. You can make it a boring band insulator, you can make it a quantum Hall insulator, or if you take two copies, if you include spin, you can make a topological insulator, and that was the first Z2 topological insulator. And so the starting point in there is something like H, if I'm expanding near one of these Dirac points in graphene, I've got two momenta, and think of this more like pseudo-spin than physical spin, but this is more or less what my two-dimensional linear Hamiltonian looks like. It has an energy like that. But this is kind of incomplete. There are various ways I could open up a gap, like just applying sigma z or something. This was in 2D. But in 3D, you could make a two-band crossing that's actually very stable. So suppose I had a point that looked like px sigma x plus py sigma y plus pz sigma z. What can I do to this? Well, it's actually pretty stable, because if I add some constant times sigma z, that's just like shifting the zero of momentum. So this is a two-band crossing that is very stable, and it's actually a so-called Weil point. And what it describes is something that was important in the early days of the Dirac equation, actually. So Dirac wrote down his famous 4x4 matrix equation for how a three-dimensional electron should behave in special relativity. And immediately after Dirac, two people figured out two different ways that you could simplify the Dirac equation into a 2x2 equation, or into two 2x2 equations. And those two ways of simplifying the Dirac equation are two of the most trendy topics in condensed matter physics, I would say, the last couple of years. One was Majorana, which I think you all know. So Majorana realized that the electron is different from the positron. The electron is not its own antiparticle. But maybe the neutrino or something like that, maybe you could have a particle that is its own antiparticle, and then the Dirac equation is simpler. And those would be Majorana fermions. Weil pointed out a different way to simplify the Dirac equation. And for a long time, we actually thought maybe the neutrino was one of these, but now we know it has a mass, so it's not. Basically, if you have a massless particle, think about what we wrote here as p dot sigma. That's like saying there's a definite handedness to the Hamiltonian. P and sigma, the momentum and the spin want to be parallel. Weil's point was that if you've got a massless particle, then if its helicity, if its spin along the direction of motion, say, is positive in one frame, then it's positive in every other frame, because a massless particle, you can't catch up with it, you can't boost faster than it and flip the helicity. So in other words, a normal particle like the electron with the mass, what its helicity is changes depending on how you're looking at it, but not for a massless particle, which is another way of saying that a massless fermion can break up into a left-handed partner and a right-handed partner, and those are really like different particles that don't get converted. So for example, we thought for a while that maybe neutrinos are always left-handed. Now we know that's not true, but it was reasonable until the 1980s or so to believe that. So we don't think we have them as fundamental particles, but we do have them in three-dimensional solids, and we think they have some interesting responses. In particular, in this class so far, you've learned about E over H responses and E squared over H responses. something we worked on a lot the last couple of years. We think that there is a response in these Weil semimetals that is the first example of an E cubed over H squared response in some optical property. And there's a little bit of experimental evidence, but it's not quite clear. So that's one direction, topological semimetals. But a reason why this is hard is that in the topological states we talked about, there's a gap and there's a notion of kind of adiabatic transport like pumping. And that makes life a lot easier. You don't need to worry too much about disorder and things like that. The stability of states like this is a lot more complicated to show in a real world with disorder. So for example, I would have one Weil point with p dot sigma, but there's another point somewhere in the Brillouin zone with minus p dot sigma. Let's call this one plus and this one minus. And if those mix strongly enough with each other, then they can disappear. So they're not quite as topologically protected. Another way to look at this, I didn't write down this formula so far, but there's a neat trick to argue that at least the definition of the integer Hall effect remains with disorder. So if I looked at the integer Hall effect definition of, so this is a side comment on how to generalize TKNN to interactions and disorder. Before, we said that this was some integral like 1 over 2 pi, this was the Chern number, d2k of, well, if I were going to write out the Berry curvature, du dky minus Hermitian conjugate, then I. So this is writing out the Berry curvature in terms of u, but this was a one electron state as a function of momentum. So it kind of assumed that momentum was well defined and assumed one particle. If I give you a many electron state, there's a different way to use the same mathematics to define a kind of many particle Chern number, which is also sigma xy. And that is, well, the 2D Brillouin zone is a torus. Suppose I just thought about putting my physical system in real space on a torus. And then I could do the following trick. I could imagine putting a magnetic flux that passes through this circle of the torus. Call that, say, phi 1. And I could imagine another magnetic flux that passes through that circle of the torus, phi 2. And I could compute, let's call it C twiddle, as 1 over 2 pi, integral over these fluxes of how does the many electron wave function respond. And why do I do this? Well, at the one electron level, so if I were talking about a Slater determinant, if this many-body wave function were a Slater determinant of one particle wave functions, actually, the problem that you solve in band structure, although you don't usually think about it this way, is exactly this problem. Because, say, if I'm thinking about a 2D unit cell, what happens when I hop to the next unit cell? Well, I put myself back in the same unit cell, but there's a cost like e to the ikya or something. Basically, this is my flux. So in other words, you don't usually think about it, and this idea is from a 1985 paper by New, Thallis, and Wu. It's called the Flux Trick, usually. Even though you don't think about it this way, whenever you solve a band structure, you're actually solving this problem, where the torus is your unit cell, and these fluxes are factors like that you pick up when you go from one unit cell to the next. But at least in principle, that's not limited to one electron, and you could make a many-particle Berry curvature and compute this, and that's, maybe the beginning of an argument about interactions and disorder that unfortunately we don't have time for, I suppose, but I just thought I would mention that some of what I've said, even if it started with one particle, generalizes pretty quickly to many particles or disorder or whatever. And then the last comment I was going to make about something you could read on your own is another kind of topological state. I would say the two simplest fractional topological states, the so-called hydrogen atoms for fractional topological states. So one we've already done, which would be like the nu equal to 1/3 Laughlin state. And the other, and here if you want to reference, there's some lecture notes by Kitaev and Laumann that I think are nice. They aren't the discoverers, I mean, but they have a very nice set of calculations. The Z2 spin liquid. And this is Z2 in a different way from the topological insulator. And this is what I said about the simplest example of a fractional topological phase that doesn't have to have an edge. It doesn't have any preferred chirality or anything like that. It's got two kinds of particles, two quasi-particles, and each one creates a pi statistics with the other, which is called semyon statistics. So in other words, if you were going to make a so-called K matrix like what we talked about before, it looks like 0, 2, 2, 0. That's a way to make a Chern-Simons theory for the Z2 spin liquid. And the thing about this, which is really neat, and the reason why that would be an exercise that might be worth your time, is you can actually make a lattice model and do the braiding in the lattice model with explicit calculations and see how this pi relative statistics appears. And that lattice model is usually called the Toric code because it also appears in quantum computing stuff. So that, I think, is kind of what I wanted to accomplish. You learned a bit about integer and fractional topological states. I think it's a beautiful field. I think there are a lot of developments still happening. I don't want to give the sense that everything is done, especially in 3 dimensions. We think there's stuff out there that we don't understand. So for example, no one has a good fractional state in 3 dimensions in any kind of experimentally realistic Hamiltonian. So hopefully someone from your generation will figure that out. With that, any questions? Otherwise, you get a few more minutes before the next talk. So I'll be around. Yes, question?
Can you do a Chern-Simons theory also for higher order topological spaces?
I don't know. My suspicion is that there's kind of a dimensional reduction sometimes in theories where you can make a theory that might be relevant. Sometimes like a Walker-Wang model would be an example, which is a 3 + 1 dimensional thing, but it's kind of like an object whose surfaces would be 2 + 1 dimensional Chern-Simons theory. So I think the key might be to make a theory that would live in d dimensions, but its main consequences would be on d-1 or d-2 dimensions, which is kind of my superficial impression of how the higher order TIs work. But I don't think I've seen a paper on it. Good. Other questions? Going once, going twice? Oh, yes. Well, okay. Well, I count disorder as like impurities. Okay, so there's sort of topological defects, which would be very strong impurities. Some states generalize naturally and some don't. And okay, so there's maybe a theoretical question and experimental question. So theoretically would be, can you still define the state even with disorder? And that's pretty hard in the metallic case, actually. So for example, with the Weil semimetal, that sort of starts from the idea of 2 different points in momentum space. So if momentum no longer makes sense, you have to be a little bit careful about what does a Weil semimetal even mean. So that would be a case where you'd worry about disorder. There are other cases, like the integer Hall effect. You could actually use this to think about, I can put my system on a torus and it might have impurities or whatever, but I could still try computing this integral. And if this integral gives me a non-zero integer, then I would say even with the disorder, it's still in that topological phase. But then there's the experimental question of how strong can the disorder be before you destroy it. And people spend a lot of time doing calculations on that, but it's a little bit hard to give some kind of universal answer. So I think that's where we are. All right. Oh, yes.
How does fractal topological order fit into the picture of forms?
I think we're still understanding. So fracton phases, okay, there's one class. I think there's sort of 2 different families of fracton phases at least. There is one class where we kind of understand the field theory limit, and they're related to these like tensor theories. So fields that are a little bit more complicated than the vector fields I talked about here. There's another category where I'm not quite sure whether one should really think about them as topological. So there's some topological fractons and some maybe non-topological fractons, but I think that is another example of something that people are still trying to figure out. And yeah, and with fractons, as I said, in 3 dimensions we have some examples of possible topological phases even with fractional particles, but so far, they are not, as far as I know, experimentally relevant. So one option would be to wait until the quantum computing future when people can build whatever Hamiltonian you want. Another would be maybe we can find some simpler Hamiltonian that would exactly exist in a material or something. All right, I think I'd better hand over to the next speaker, but thank you all for your attention.